Hi, welcome back to Mind Maths with Amina. Today I'm solving the practice questions given in the Statistics 1 study guide given by University of London for their EMFSS program. Question number 30 goes as follows. A company is concerned about interruptions to email. It noticed that problems occurred on 15% of workdays. So there's a 15% chance of a problem occurring, right, on any workday. To see how bad the situation is, calculate the probabilities of an interruption during a 5-day working week, okay? So the probability of a problem on Monday and on Tuesday. So the keyword here is and. So the answer is going to be the probability of x. Suppose x is the random variable that an interruption happens on Monday and Tuesday. It's going to be a 0.15 multiplied by a 0.15. So that's going to be a 0.025. Okay, part B. For the first time on Thursday. Okay, so the probability of the event y, which is an error happening first time on a Thursday, it means there was no error on Monday. So since probabilities have to add up to a 1, a problem of no problem happening is 1 minus a 0.15, which is a 0.85. So no interruption on Monday, no interruption on Tuesday, no interruption on Wednesday, and then there is an interruption on Thursday. So we have a 0.85 power 3 multiplied by a 0.15. So the answer is a 0.092. Okay, part C. Every day. Okay, so there's error every day. So there are 5 working days. So this is just going to be 0.15 to the power 5, which is a 0.000076. So it's very low chances of interruptions happening every day. Part D, at least once during, okay, let's define the variable L as a number, or maybe N should look better. Okay, number of times problems occur. Okay, so at least once. So they're asking for n being at least, so greater than equals to a 1. Since probabilities have to add up to a 1, the negation of n greater than equals to 1 is just n being strictly less than 1, which means that the probability of no interruptions happening during the week. So in all 5 days, there is no interruption, 0.85 power of 5, and we have a 0.556. Okay. The next question is 2 fair coins, 10 pence and 9 pence are tossed. So they're fair coins. Okay. Find the probability that both coins show a head. Okay, let's just create a sample, a space of all possible scenarios. So either both will show a head, or one will show a head, the other will show a tail, or the first will show a tail and the second will show a head, or maybe both will show a tail. Okay, so find the probability that both coins show a head. So we can see that there's only actually one scenario out of a 4 that this happens. So the probability that both coins show a head, or you could actually say the probability of the first showing a head is a half, and the probability of the other one showing a head is a half. So the overall probability is a 1/4. So we can say it like this as well. Okay, because they are independent events. Okay, different, okay, no, this is part 2. Okay, different faces showing up. Okay, so that happens 2 of the 4 times. Okay, but we can actually also, since the events are independent, we can do this as follows: different faces. Okay, so I'm saying the first showed a tail and this head, and the second showed a tail. So a 1 by 2 into a 1 by 2, either this or, so we have a plus sign. The first shows a tail and the second shows a head. So half into a half. So it's a 1 by 4 plus a 1 by 4, which is a 2 by 4. So the number of favorable outcomes is 2 and the total outcomes is 4. So there's a 50% chance of this happening. Okay, at least one shows in head. Okay, B, at least one shows a head. Okay, from the sample space, we can see that there are, the number of favorable outcomes is a 3. So the answer should be 3 over a 4. However, we can also do it this way, that the 3 possible scenarios are a head, head, or, let me write it this way, a head, head, or a head, tail, or a tail, head. So this is 1 by 2 into a 1 by 2 plus 1 by 2 into a 1 by 2 plus 1 by 2 into a 1 by 2. So we have a 3 by 4. Okay, moving on to part B. You are told that 10 pence shows head. What is the probability that both coins shows a head? So this is, you can say, a conditional probability question. So let's see what happens to our sample space. So this was our initial sample space, and suppose that the first entry is my 10 pence coin and the second one is my 50 pence coin. So how, given the fact that the first one is a 10 pence coin and we know that it shows a head, my new sample space is going to be a head, 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 and tail, right? So we can see the number of total observations is R2. And what about the favorable outcomes? You want to see the probability that the coin shows a head. So this is our new sample space. And what is the event that both are heads? So we can see the cardinality, or the number of observation in our favorable outcomes, is just 1. So the probability of both showing heads, given that the first coin showed a head, is a 1 by 2. Remember, when you have conditional probability, your sample space actually gets reduced to the new sample space because we are already given the fact that the first coin is a head. So these other 2 outcomes are actually irrelevant to us because we already know that the answer either is this or it's that. So this is my new sample space. Okay, part B. Part C. You are told that at least one of the 2 coins shows a head. So now our sample space changes. What is the probability that both coins shows a head? So what is my new sample space? It says that at least one of the two coins shows a head. So the sample space is either head head or head tail or tail head. So the cardinality of the new sample space is now a 3, and the event B that both shows a head is there's only one outcome in this there's only one favorable outcome, so the cardinality of set B is just a 1. So the probability that both show head, provided that at least one showed head, is favorable outcome is 1, and the cardinality of the new sample space is a 3. Okay, so the next question. At a local school, 90% of students took test A and 15% of the students took both test A and B. Okay, so the probability of A is 0.9, and the probability of taking test A and B is 0.15. Okay, based on the information provided, which of the following calculations are not possible and why? What can you say based on the data? Okay, part A, the probability of B given A. That's the probability of B intersection A over the probability of A, which is a 0.15 over a 0.9, which is equals to 0.167. Okay, part B, probability of A given B. That's going to be the probability of A intersection B over probability of B. We can't calculate this because we don't have the probability of B, which is the denominator. So yeah, we can't do this calculation, it's not possible. Okay, probability of A union B is a probability of A plus probability of B minus probability of A intersection B. We have probability of A, but we don't have probability of B. We do have actually the probability of the intersection. So again, we can't calculate this because we don't have the probability of event B. Okay. If you knew that everyone who took test B also took test A, would that change your answer? Okay, so the probability of A who took B. Okay, so given that they've taken already taken the test B, will also take A. Okay, so this means that they're definitely going to take A. So this is going to be a 1. And it would also actually mean that probability, let's do it like this. If you've taken B, then you've definitely taken A. Yeah, this is a nice depiction. So B is going to be a subset of A. So probability of A union B is just probability of A, which is a 0.9, and the probability of A intersection B is going to just be probability of B, and this was a 0.15. So it does actually change my answers to the above questions. Yeah, so the answer would be that yes, it does change my answers. Okay, because this is going to be new answer for part B, and this is the new answer for part C, and this kind of changes the answer to actually it doesn't. Yeah, it doesn't. This remains the same. Okay, so question number 20. In an audit, Bill analyzes 60% of audit items and George analyzes 40%. Okay, so Bill analyzes, the probability that Bill analyzes audit is a 60%, and the probability of George analyzing is a 40%. Okay, Bill's error rate is a 5%. Okay, an error happening. So the probability of an error happening when Bill analyzes is a 5%, so 0.05. So an error not occurring would be 0.95. Okay. What about George? It says that the error rate for George is a 3%. Okay, so the error for George is a 0.03. Okay, so that means he gets it right. He's error free, 0.97. Okay, 97% of the times he's error free. What is the probability that it is an error? So audited incorrectly. Okay, we can see that there are two ways in which we can have an error. First is if Bill makes an error. The other option is that George makes an error. Okay, so the probability of an error happening is probability that it was Bill and an error happened, or it could be that it was George and an error happened. So this is probability of the audit being done by Bill and the probability of error happening provided that Bill was doing the audit. Similarly, probability of George, probability of error given George. Okay, so we have a 0.6 into a 0.05 plus a 0.4 into a 0.03. Okay, so our answer would be 0.042, which is 4.2%. So the probability of an error is kind of high, I would think, but not that bad. Okay. A and B. If the chosen item is incorrect, what is the probability that Bill is to blame? Okay, so we want to, we already know that there's an error. What's the probability that it was Bill's fault? Okay, so we want to see the probability of Bill making the error over probability of an error. So this is simply 0.6 multiplied by 0.05 over a 0.042. I've just used the formula. So 0.71. So there's a huge chance that Bill is to blame for the error. Okay, the next question. Question number 22. The probability of a horse winning a race is 30% if it is dry. If it is dry. Okay. So either the weather is dry or it's not dry, so it's wet. And there's a chance that he's going to win or he's going to lose, which is the complement of winning. So winning, not winning. So the probability of a horse winning given it's dry is a 0.03. Okay, so the probability of winning given it's a dry day is a 0.30. Oh, sorry. It says if it is dry. Yeah, okay. That's right. And 0.5 if it is wet. Okay, so a probability of winning when it was wet, which was the complement of dry, is a 0.5. Okay, so the probability of not winning when it is dry would be a 0.70, and the probability of not winning when it is not dry is going to be a 0.5. Okay, find the probability that the horse wins. So he's either going to win when the weather is dry, or he's going to win when the weather is wet. So the probability of winning is that the weather was dry and the horse won, or the weather was actually wet and the horse won. Okay, so this is the probability of dry multiplied by probability of winning given dry plus probability of wet, which is not dry, into probability of winning given wet weather. Okay, so we have oh, do we even have the probability? Oh, the weather god gives the chance of rain as 40. Okay, so this means that there is the probability of raining, so the weather would be not dry would be a 0.4. So we have a probability of dryness being a 0.6. Okay, so a 0.6 into a 0.3 plus a 0.4 into a 0.5. Yeah, so I think this should give us the right answer, and it should be a 0.38. Okay, part B. If you are told that the horse lost the race, so given that the horse lost, so the complement of winning, what is the probability that the weather was dry on the day of the race? So weather was dry. Okay, so what we need to know this time is the probability of the weather being dry and the person losing over probability of losing. So since probabilities actually have to add up to a 1, that means probability of winning plus probability of not winning should be equals to a 1. So probability of not winning is going to be 1 minus a 0.38. Whereas the probability of dry and not winning is probability of dry and then probability of basically losing given the dry weather. So the probability of dry is weather is a 0.6 into and not winning when is a 0.7. Okay. Okay. So then the answer would be a 0.6 into a 0.7, and that should be a 0.62. Yeah, so our answer would be a 0.6774. I wonder why the horse Why is it so that the horse loses when the weather is dry? Strange. Okay, we're done with question number. Okay. 23. A restaurant manager classifies customers as well-dressed, casually dressed, or poorly dressed. Okay. As well-dressed, casually dressed, or let's just remove well-dressed, casually dressed, or poorly dressed. The probability of well-dressed is a 0.5. The probability of casually dressed is a 0.4. The probability of poorly dressed is a 0.1. I don't like this, but okay. Okay, the manager found that wine was ordered 70% of the okay, so wine, what do I call it? Wine was ordered, okay, ordered, this looks ordered. Okay, so wine was ordered given that the person was well dressed was 70%, so a 0.7. So when they weren't the wine was not ordered, how many times? Only 30% of the well-dressed people did not order wine. Okay, so we'll have to write down the probabilities over here as well and over here as well. Okay, so the probability of ordering wine when you are casually dressed is 50%. Okay, and the probability of ordering wine when you are very poorly dressed is a 0.3. Okay, so since probabilities have to add up to a 1, therefore we can find out the complement of each. Okay, what is the probability that the random chosen customer orders wine? Okay, so there are 3 possible scenarios, right? You either order a wine when you're well dressed, or you could be ordering a wine if you're casually dressed, or you could be ordering a wine when you're poorly dressed. So the probability of ordering wine is that you could be well dressed and you could be ordering it, or you could be casually dressed and ordering wine, or you could be poorly dressed and still ordering wine. So this is probability of well-dressed multiplied by probability of ordering given well-dressed plus probability of casually dressed multiplied by probability of ordering wine given casually dressed plus, last but not least, probability of poorly dressed multiplied by ordering wine given that you're poorly dressed. Okay, so we have a 0.5 into a 0.7, then a 0.5 into a 0.4 plus a 0.3 into a 0.1. Okay, so we have a 0.58. So 50% chance that any of these customers, any customers of this restaurant is going to order wine, which is a high, more leaning towards ordering wine. If wine is ordered, what is the probability that the person ordering is well dressed? Okay, so what is the probability that a well dressed person has ordered wine? So this is the probability of well dressed and ordering wine over the probability of ordering wine. So well-dressed person ordering wine is a 0.7 into a 0.5 over a 0.58. So even 0.60% chance. Okay. Part C. If wine is not ordered, what is the probability that the person ordering is poorly dressed? What is the probability of a poorly dressed person not ordering wine? So you want to see the probability of poorly dressed and not ordering wine, or probability of not ordering wine. Okay, so a poorly dressed person not ordering wine is a 0.1 into a 0.7, and since probabilities have to add up to a 1, this is just 1 minus a 0.58. Okay, so this is going to be a 0.07 over a 0.42, which is approximately 0.17. So there are a number of other questions given in the study guide, but they follow the same logic and they follow the same pattern as these ones. In the next recording, I will start chapter 4 of the study guide, which is basically how to convert the x variable, which is normally distributed, to a z variable, which is normally distributed with mean 0 and variance 1. So basically a standard normal distribution, and how to find probabilities, how to use the statistical tables and stuff like that. So this is all for probability. I hope this was beneficial, and I'll see you in the next one. Take care.